Hi, my name is Hsia Yeo, and I am an NPP with the leader team at Goddard. Yeah, and I would like to share today some experimental, don't do that, some experimental results straight out of our lab, and it's on the hydroxylation of lunar soil with solar wind protons. The motivation for this, I think, is really well known. We've talked a lot about this hydration feature in the 3 micron band. Shout out to the Moon Mineralogy Mapper. So I think a really natural next question to the discovery of widespread hydration on the lunar surface is, how did it get there? And that's the question that I'm going to try and sort of how to answer with this study. So there are a number of theories for how hydration got to the moon. The one we are examining today is solar wind hydroxylation, which I'll go into in a little bit, but there are other theories around, including micrometeorite bombardment or cometary bombardment. And this is a really interesting scientific question, but it's also very relevant to exploration purposes, especially if we are trying to develop some sort of long-term human habitation on the moon, knowing whether where the hydration comes from will tell us a little bit about how renewable this resource is. So I think it's like super relevant for this community. What is hydroxylation? And I found this super cute cartoon and I thought I'd share it with you. The sun is a source of really high energy protons, and it's continuously impacting the lunar surface, which is rich in oxygen. And so there is a chance when you have this really energetic protons hitting this oxygen that hydration or OH bonds can form. And we want to study this phenomenon. We have a bit of evidence in the community for solar wind caused hydroxylation, and the most one of them is that the lunar surface is observed to lose OH or H2O in the morning, but return to dawn levels by the evening. And so this kind of suggests to us that there's some sort of source of hydration during the day. Could be solar wind. And another piece of evidence is if you look at the bulk hydration, such as using a neutron spectrometer on the lunar frost vector, you see that it is only weakly correlated with the hydration as observed by M-cube. And this kind of hints to us that the hydration is only found close to the surface and maybe a superficial process, such as the solar wind, is a likely source of this hydration. So previous experimental works have measured hydroxylation before and after proton irradiation, but not during irradiation itself. And this is the gap that this study hopes to sort of fill. So here's our experimental setup. Don't be afraid because I have drawn a diagram for it. So, you don't have to freak out about how messy it looks because it's very simple here. We have our sample and we keep it in a vacuum chamber. And then we use an ion gun, and it's a KeV ion gun that shoots high energy protons at our sample. And during this process, we have an infrared light source that is shining onto our sample, and the light that's reflected from our sample is collected by a series of parabolic mirrors, and it goes into our infrared detector. So a quick word about our samples. We use 2 Apollo 17 era samples, and the main obvious difference between them is one of them is very immature and the other one is very mature, and we compare these two to a control of crushed silica. All our samples were prepared by baking in vacuum at a high temperature and low pressure to remove any adsorbed hydroxyls, both internal and external. So lo and behold, we do see the OH band at 3 microns get enhanced as we radiate the sample. So what you're seeing here is both the aged, the older sample on the left and the younger sample on the right, and both of them with increasing durations of hydrogen irradiation. The 3 micron band does grow. And one observation you can make from these 2 samples as you compare them to the crushed silica control on the top right is that they are a lot broader in their features as compared to the crust silica sample, which is kind of in agreement with what we observe on MQ. And I think it's really interesting. We should delve into why it is that these bands are a lot broader than our control. And a quick note is that these samples were irradiated for about a day in our lab, and that kind of corresponds to about 15,000 years on the lunar surface in terms of the fluence that it received. Okay, so, and then we did something to further probe what's happening with our samples. So first we irradiated it for about a day, and then we stopped the irradiation and we heated our sample to the lunar day side temperature of 140 Celsius or so. And we left it there for about 24 hours. We turned off the heat, and then we irradiated the sample again. And we can make some really interesting observations to see what's happening when it comes to hydration within this sample. So if you compare the maximum depth to which the band grew before heating the sample, and you compare it to the minimum, so the earliest, I can't point, but like that sort of shows you that the depth of the band sort of shrinks a little bit on the second set of irradiation before continuing to grow as we irradiate the sample. And then maybe another way to look at this is that we can take a cross-section at about 2.9 microns before heating and after heating and plot them all on the same graph. And maybe this illustrates my point a little bit better, which is that on the x-axis, there's irradiation time. On the y-axis is the band depth. So in run number 1, before heating, the band depth grows pretty rapidly and then starts to slow down. And then we heat the sample and the band depth shrinks a little bit and then continues to grow with subsequent irradiation. And this is really interesting to us because we think it is evidence of, right here, hydrogen diffusion. And let me explain why we think this is the case. So our infrared detector can sense to a depth of about 10 microns, but protons are only deposited on a sample to the top tens of nanometers. So when we irradiate the sample, hydrogen is implanted only into the upper layers. And if we give it time and we give it a little bit of heat, we think that the hydrogen can diffuse deeper into the sample, but it can also diffuse out of the sample and escape. And all this is being detected by our infrared spectroscopy. When the hydrogen escapes, that causes the band to shrink a little bit, which we observe. And any additional irradiation can take place when the sites that were close to the surface are kind of vacated by the migrating hydrogen. And so more hydroxylation can take place. And that's why our band continues to grow with further irradiation. So we did this again with our younger sample. And this time we went through kind of 3 rounds instead of 2 rounds of, irradiation. And we can do a similar analysis, taking the depth at 2.9 microns again and plot it together on the same graph. And between runs 1 and 2, we did not see a reset in the band depth, but between runs 2 and 3, we did. This is so puzzling to us. We're not quite sure what's going on, but definitely more studies are needed. It could be the mineralogy. We're not quite sure yet. Stay tuned. But if you take away anything from this talk, there are 2 main points here. The first point is that we observe experimentally in situ hydroxylation of lunar soil with solar wind energy protons. And the second is we think we found evidence of hydrogen diffusion within our samples. So here's a quick peek at the next and current steps that are happening in our lab. Obviously, we want to be able to quantify the amount of hydroxylation that's taking place as functions of fluence and temperature. And the sneak peek of our graphs here shows work that was just done last week by our intern, Zach, who's sitting there. And all these graphs that I showed you in the previous slides, they were taken at room temperature. But we can also heat the sample and try again with irradiation. And we still see that the band does grow, the 3 micron band does grow when we irradiate the sample at an elevated temperature, but with sort of like a different rate than the 25. And that's probably because of different rates of hydrogen diffusion happening. We're going to try this again at the lunar dayside temperature of 140 Celsius or so. And hopefully we can start to understand the dynamics that's happening within our sample. Which brings me to how it's so important to compare all our data to the hydrogen diffusion models out there. And so that's definitely something in the works. And of course, we want to understand how the mineralogy, the size, the age of our samples is affecting the shape of our hydration bands. And that's it. Thank you.